Hello, my name is Cainã Figueiredo, and I'm a graduate student in computer engineering at the Federal University of Rio de Janeiro in Brazil. Today, I will be presenting to you a work entitled Software Vulnerabilities, Products and Exploits, a Statistical Relational Learning Approach. Here is how this presentation is organized. We begin with a brief introduction. Next, we discuss some important background knowledge. Then, we justify our motivation for the use of statistical relational learning. We follow with a description of the methodology used to prepare the dataset, and then we talk a little bit about our experiment. Not least, we'll show you how we were able to extract simple insights from the model. We then ran through some related work and finally conclude the presentation. One of the main concerns with vulnerable products is the potential use of exploits to cause damage or misbehavior, and in fact this is a justifiable concern as it is observed that several exploits are released daily. Furthermore, these exploits have become so complex that it shows us that the techniques for their creations are becoming quite advanced. And all of this poses a major challenge when it comes to determining the likelihood of a vulnerability or a product being exploited. And even more urgent, industrial control systems have some requirements that make it difficult to apply traditional security solutions. So, for example, it would be necessary to pre-schedule the system outage in order to apply a patch or even an update. In the literature, we can find a number of approaches that are designed to address vulnerability exploitation, but a product level view is not as studied. So how could we extend these approaches to consider product weaponization? A straightforward solution would be to simply look for the presence of any exploited vulnerability in the products to serve as an indication of this issue, but this is unreasonable due to some factors, and the first factor is that exploits may need to make use of multiple vulnerabilities to be effective. Therefore, if the product contains only some of these vulnerabilities, it will not be enough to enable an exploit event. On top of that, exploits can take advantage of some specificity of a version of a product, and even if vulnerabilities are present in multiple versions of a product, exploits may be available only for a subset of these versions. Therefore, we present our goals. Given information about vulnerabilities, products, and exploits, we tried to answer two questions. First, we are interested in understanding the feasibility of determining relationships between products and exploits from information about relationships between products and vulnerabilities and between vulnerabilities and exploits. And that done, what kind of roles govern these relationships, particularly with a focus on industrial control systems? To answer these questions, we extended the dataset used in a previous work by introducing new information, and then we use statistical relational learning on this data, and through model interpretation we also extract some insights on the data. Let me introduce you to some concepts now. Firstly, I'm going to talk about statistical relational learning, which is a subfield of artificial intelligence and acts exactly in the intersection of these three dimensions. That is, it allows learning to be carried out in a complex domain where there are several heterogeneous objects and relationships between these objects, and where there are uncertainties about this information. From this field, we choose to use the Relational Dependency Networks Boost model because it usually presents in a reasonable time, performs superior to state-of-the-art approach, and it has an implementation in a system called Boost SRL, and this system requires the input data format to be specified through first-order logic predicates. To compose our data, we used the dataset introduced in a previous work, and in that dataset we found ICS products and corresponding vulnerabilities collected through the search engine called Shodan. And for our work, we filtered the products so that we kept only those labeled as ICS. As a result, our base contains 156 products from a number of vendors. Then we extended this dataset by adding some information. First, we updated the product vulnerabilities list using the NVG repository. Later, we included exploits from the exploit.db base that exploited the vulnerabilities of these products. Finally, we collected the exploits that affect our products by leveraging information about exploit.db and Google queries. And why use statistical relational learning? Imagine that you had one of your products exploited and then you are looking for what caused it to happen. Fortunately, you are faced with the following statement. This product was affected by this exploit because of that vulnerability. Since a representation of this information through traditional machine learning methods is not so clear, we can easily reduce this sentence to these three first-order logic predicates. Product P has vulnerability V has exploit E, and product P has exploit E. And this image nicely sums up this last observation, where the figures represent the entities and the arrows represent the relationships between them. And we are interested in inferring the relationships between products and exploits from these other two relationships. It is important to emphasize, however, that these relationships is not transitive. And to give an example, it would be the case that the exploit needs to take advantage of multiple vulnerabilities. Also, our data is incomplete, hence it is common to find, for example, exploits that do not refer to any vulnerabilities. Our approach was motivated by the lack of data transitivity and completeness. Now let's see how we prepared the dataset to the Boost SRL format. In this table, we present the mapping between collected data and produced predicates. In the first column, we have our entities, and each entity has a set of attributes that were also collected during dataset construction, and from them we generated predicates of the form predicate name, entity ID, attribute value, and in the case of the vulnerability severity, for instance, we could have a predicate like CVSS severity with the ID of a vulnerability and its severity. Finally, the relationships between products and the vulnerabilities and between vulnerabilities and exploits gave rise to predicates of the form predicate name, entity ID, entity ID. Let's take the relationships between products and vulnerabilities as an example, and we would then have something like product has vulnerability, Siemens Symmetric S7-1200, with the idea of vulnerability. We also used a library called RNLP, which means Relational Natural Language Processing, in order to extract facts from textual descriptions of vulnerabilities. And at a high level, this library generates predicates that capture the relationships between words, sentences, and blocks. Now, what will the model try to predict? We propose two alternative target predicates. The first one is product has exploit, and as a product can have multiple exploits, each of these associations will produce an instance that will be placed in a set of positive examples. And for the generation of the negative examples, we generate all the combinations between products and exploits that are contemplated in our base, and all pairs that are not in the set of positive examples are then considered as negative examples. We can see that this produces a very unbalanced base. In contrast, the next target predicate product has any exploit leads to a base with less aggravating imbalancing, and in this predicate we are only interested in whether the product has an exploit or not. If it has at least one, then an instance of this predicate is added to the set of positive examples. On the other hand, if it doesn't have any exploit, then an instance of this predicate will be added to the set of negative examples. And about our experiments, our methodology was as follows. We started with a model generated from a reference configuration, which we call baseline model. We then refined and extended the previous setting that has the highest value for the AUCPR metrics so far, and each evaluation is done using 5-fold stratified cross-validation. And this is our baseline model. It is the simplest and most straightforward model, since we are only considering the relationships between our entities, represented here by the arrows. And the red arrow represents the current target predicate, that is, product has exploit. We've kept the imbalance for now, and this table summarizes everything we've talked about so far, and also reports the performance achieved by the model in terms of the metrics AUC-ROC and the AUC-PR being 0.86 and 0.31. In the next experiment, we will try to increase the AUC-PR metric. As a first attempt, we tried to change only the target predicate to product has any exploit. By putting the results side by side, we can see that this change favored the AUCPR metric, as predicting the exploitation of a product is a simpler task than pinpoint the exploit. And following our methodology, experiment 1 will be chosen and refined to give rise to the next experiment, since it has the highest AUCPR. And this time we considered the balancing of classes as a refinement, but no improvement was observed, and for this reason we still continue with experiment 1 as the starting point for our next experiment. And now you consider the insertion of entities attributes, represented here by the coloring of these figures. And as you can observe, it was possible to improve both metrics, and to generate our last experiment we take as a starting point the configuration of experiment 3. This time we also considered the information extracted from textual descriptions, thus obtaining a performance gain again. And in summary, we can see that it is feasible to determine the relationship between products and exploits, and for this it is useful to use information beyond simple relationships. I believe we can already see how interpretability can be addressed in our approach. And for this purpose, we resort to the structure that is produced as output from RDN Boost, which consists of a series of relational regression trees, including a combination of them. And for ease of understanding, we present here a simplified version where internal node contains descriptions in natural language and leaves report the fraction of weaponized products. The first interesting pattern that we can observe is that if an application product has an exploited vulnerability, then the probability of weaponization is at least 0.54, and it can reach a probability equal to 0.62 if there are no vulnerabilities with high excess complexity. This fact reinforces the lack of transitivity in these relationships. On the other hand, we see a drop in the probability of weaponization when the root test fails. The only exception here is with FritzOS operation system, which highlights the fact that our relationships data is incomplete. Even in this case, our approach was able to generalize roles using entity attributes as well. In our paper, you can find a more in-depth discussion about insights. Before we conclude, let's look at our work in the literature. We have identified 3 main related areas, namely cybersecurity, industrial control systems, and statistical relational learning, and our work contributes in these 3 areas. Finally, we highlight the conclusions of the work. First, we saw that it can be essential to fusing together data about products, vulnerabilities, and exploits. We then showed that statistical relational learning can be used for this purpose. In particular, we were able to build a complex knowledge base, and using our approach, we were able to infer unknown relationships between products and exploits with an AUC ROC of 0.83 and an AUC PR of 0.69. Finally, we indicated that it is possible to extract useful insights from the model. And with that I finish. Thank you all.